I am an ecologist, first and foremost. I became a mathematician, although if you talk to a mathematician, they would probably laugh at that terminology. I became one through practice and application. Now, these days, I'm mostly a modeler. So I'm coming at this from a very applied direction. Oh, that was my pie joke, so I didn't put it through. The most important things to realize is that modeling, in general, models are abstractions of reality. They're necessary simplifications. You cannot predict exactly what something will do. We generally try to use these to look at what kind of underlying mechanisms could lead to such and such a phenomenon. And all models are wrong, by definition. Some are useful, many are not. And these are just variations on that theme you can see here. Another fairly famous ecological modeler, the huge possum we call him, Hugh Possum, said this several years ago, and it's a bit extreme, but in my view as ecologists, what we do is we go out in the field, or we employ people to do that, as in my case, and they collect data, and those data are then, they're numbers, they're measurements of things, and they go into a database, and then we use models to figure out what's going on in that system based on the questions we pose and the hypotheses we set up. Now, that means that fundamentally all ecologists are mathematicians. And if you can't consider yourself in that role, then I don't think you can call yourself an ecologist these days. With the massive amounts of data out there, we are essentially become the mathematical application of natural history. Now, that doesn't mean there isn't any room for naturalists out there. We need people to identify things and collect things, but fundamentally, if you want to call yourself an ecologist, you are a modeler, therefore you are a mathematician. Now, who can tell me what those two equations are? Steve Dilleen's not allowed. Anyone? Two most famous equations in ecological history. Any idea? It's kind of embarrassing, isn't it, that a room full of ecologists doesn't know the two most famous equations in ecology. Any guesses? Stabs in the dark? Those are the Lotka-Volterra predator-prey interaction models. Differential equations. Number of prey is a function of the number of predators and vice versa. Very simple. Some of the first really famous, at least within our discipline, ecological models. Now that you all feel very embarrassed, you can remember that next time. So the way I'm going to do this is I'm going to talk about some paradigm differences in statistics in general and how we generally are starting to apply them more and more in ecology, and my views on some of those, and they're pretty strong views. I never have been known to keep my opinions to myself. Model comparison techniques, and then things like evidence ratios that should supplant such terrible terms such as significance. And talk a little bit about model averaging. That's the approach of taking model uncertainty into account. Sort of the very basic differences between maximum likelihood and Bayesian approaches. And then probably the most useful tool to an ecologist is the generalized or general linear models. Generalized is just different error distributions, and I'll go through that. And then maybe some applications, and I talk about something that Steve has actually been very helpful with, and some phylogenetic versions or analogs to general linear models. And some old ideas, some new applications of those, going on to what is probably more and more important in ecology is getting into the socioeconomic aspects. And that's more on the applied side of things, conservation, valuing nature for something other than just its intrinsic value, its economic benefits, also perhaps its health benefits to humans. And then finish off with another very useful tool, at least in my career, is things like matrix models and population projections, and give you a host of examples of all of those. So, who here has taken an undergraduate course in statistics of some description? It may not have been called statistics, most of you, right? Well, this is probably what you were taught, the Neyman-Pearson null hypothesis testing paradigm. Now, that really asks the question, could the observations I've just collected, or more extreme ones, it depends on how you pose the question, have occurred by chance? And that's the fundamental approach to most frequentist models. Now, it's used primarily for binary in a sense, not a binomial, but a binary detection of a problem. So you have a null hypothesis, which poses that the two things that you're comparing, this is the binary aspect, are equal. So in this case, it may be the mean height of individuals in two populations. The alternative hypothesis can be, well, the alternative hypotheses can be myriad, everything from they're not equal, or one's less than the other, one's greater than the other, or one's different by a certain margin. Now, under the null hypothesis, the Neyman-Pearson NHT paradigm, you either fail to reject the null hypothesis or you reject it. That's it. There is really no way of examining the alternative hypotheses explicitly. So the probability of a false alarm is fixed at generally some arbitrary value. That means the probability that I've rejected or failed to reject that null hypothesis. And that is usually what we call the type 1 error, what I call the false alarm error. Now, you might have heard of that before, and we'll get to that shortly. So that this p-value that you might have heard of is if the null hypothesis is true, it asks what's the probability of observing the metric at least as extreme as the one observed. So that the alpha, or this p-value, is the threshold probability below which we agree that this p is significant, inverted commas. In other words, that the null hypothesis is ruled as false. Now, my view on this is that it is perhaps the ugliest word in science today, and that's this, significant. I argue that it has absolutely no value at all in science anymore and should never be invoked. For example, we use the standard 1 in 20, and it is very much a hangover, and a terrible hangover at that one. This is the probability, 5%, 0.05, I'm sure you've all heard of this before and used it yourself. It says that above the 1 in 20, we're going to reject the null hypothesis, or fail to reject the null hypothesis, depending on your question. Now, why is 1 in 20 important? Why is not 1 in 19? I mean, what's magic or wonderful or mystifying about 1 in 20? Well, it's no different from any of these. You choose because it's entirely arbitrary. It means nothing. And you'll hear this on the radio. All politicians use it. Everyone who tries to sound a little bit more sciencey or technical when they give an interview, they say there was a significant decline. Well, does that mean that it halved and you had one animal and then you had none, or did you have 3,000 and then it went from down to 2,500? I mean, what does that mean? First of all, you've not quantified what the decline is. I argue always should quantify what you're talking about. Second is you're imparting some sort of judgment by invoking this term. And then this sounds more technical and you sound more savvy about what you're talking with the interviewer. Things like this, there are significantly more. Well, 6 is significantly more than 5 if you don't have a lot of uncertainty. And then a corker, it's very non-significant. So very in itself is also a ridiculous word, should never be used in science. And coupled with significant or its meaningless negative form just means that this sort of spirals into some useless jargon that means different things to different people. We're scientists, we're supposed to be unambiguous. And I believe that the Neyman-Pearson null hypothesis testing paradigm has pushed us into this meaningless sphere. Continuing on, so the flip side of the type 1 error, of course, is the type 2 error, which is the probability of making an error when failing to reject the null. In other words, that the null hypothesis is true. But standard techniques, null hypothesis testing paradigms cannot evaluate this probability. Now, there are post hoc methods to determine what we call power, which is 1 minus the type 2 error. And that they have some success, but they generally require more arbitrary decisions about what is appropriate, both in terms of what we consider real and what we do not consider real. For example, another extremely arbitrary term is that over the years, I don't know how it happened, but power of 0.8, that is 1 minus 0.2 type 2 error, is somehow acceptable. It's about as arbitrary as 1 in 20 for the type 1 error. It means nothing. So I'd argue that even the post hoc tests themselves have all the same flaws that the that the actual evaluation of the type 1 error is. So just to summarize, there's this complete disconnect between estimates of type 1 and type 2 error. You can have conflation of effect and sample sizes. For example, if you have lots of data and you say that 3002 is significantly different than 3001 in one population, you have very little error because you have so many data. Well, yes, there is a very small probability of buggering up, essentially, is what you're saying. But you tend to conflate that is actually an important effect size, when in fact it might be absolutely nothing, of no biological importance whatsoever. There's the ambiguity regarding how much of making the error is acceptable, as we've talked about. And there's a reduced opportunity for control in biology. In other words, that these not being able to test the alternative hypothesis explicitly seriously negates the power of your experiment, such that it only considers one dimension of the problem. The alternative and rapidly gaining paradigm in statistics, and again, it is another paradigm. In 100 years, we might come up with something entirely better, in which case we might go to more systems thinking, more complex models that don't rely on specific thresholds of any description, or even very simplistic comparisons between models. But this particular paradigm actually has been around since about 1890 with Thomas Chamberlain, called the multiple working hypotheses. So basically summarized that no more, as we said in the first slide, that because all models are wrong, there is substantial uncertainty among models, and that they should be considered in tandem, so that your abstractions or simplifications of the universe should be contrasted and considered as forms of uncertainty in themselves, just as much as the parameter estimates from a particular model have uncertainty. So, because a single alternative doesn't suffice, you consider a whole suite. These are called working hypotheses. And it really asks these two questions. What is the full explanation? Is this the full explanation of what's possible? And are we seeking to establish prematurely the truth of a single factor when consideration of more than one may be more appropriate? So you can actually go back to the original 1890 paper by Chamberlain. It's a fascinating read. Now, it's often very attractive to pin your conclusions on a single or simple explanation. It makes life easier. It's easier to tell people who aren't experts. It's easy to tell people who are outside of your discipline. But this, I think, is the fundamental flaw of traditional statistical approaches. You can account for cascades or sequences and emergent properties in multiple working hypotheses, things that you didn't actually originally pose in the hypothesis itself. And I'll explain how that might work. There's actually no restriction on the number of models you can examine simultaneously. However, it is still sample size dependent in that you don't want to test more models than data that you have. Because you can pose models till the end of time, but at some point it becomes a fool's errand. Models are ranked on relative support, and relative is the important term here, because relative means that under many multiple working hypotheses frameworks, that you're assuming that truth is somehow represented in your model set. So of the models you're comparing, you implicitly assume that there is some truth, but you might not have fully encapsulated it. So you're talking about the relative impact or support for these models to the others that you've considered in the set, not to all models in the universe, because that's impossible. And it really gets the heart of parsimony here too, because the models are not only ranked by their explanatory power, but also by their complexity. So what we're striving for is the Occam's razor kind of ideal, where we want the most comprehensive solution with the least amount of complexity. So the more you add parameters into a model, of course, the more potential explanatory power you might have, but it could be spurious, and that's just explaining random noise. We try to make that balance with multiple working hypotheses. So the first step really is to define the hypotheses to test, because every model is in itself a hypothesis. It can be a complex one, but every model you pose is a hypothesis in its own right. And you construct those models from plausible biological mechanisms. Now, we're not operating in a vacuum when we create or establish a model to test. We're usually basing it on many, many decades, sometimes centuries worth of information and data. Now, this is the real artistic component of it. It's the least mathematical, in that you can spend the rest of your life learning the flair of posing the appropriate model set. And it really is something that comes from experience. I have a lot of people get stuck on this step because they say, well, I don't know how to construct the models that I'm going to test eventually. I don't know what's appropriate. The easiest way to start is to pose all subsets, which means that you pose all the models you possibly can for the amount of data you have. But then again, it becomes a bit of a fishing exercise. Now, that might sound a little bit vague, and it is. It really is. There is an art form to posing a restricted set of hypotheses that you can compose into models and then test simultaneously and in comparison. Remember that it is not a falsification approach, a relative evidence, such that each model has some truth in it, but some are more true than others. And it incorporates the uncertainty directly of the model into the parameter estimates, especially if you're doing things like model averaging, and I'll explain that a little bit more later. And it's not just the uncertainty in the model parameters. For example, there's uncertainty in the mean of a sample, because that is a sample of a larger population. You can't measure every single individual in a population. So the estimate of the mean is that. It is an estimate, and it has an associated uncertainty. We call that the standard deviation if we're measuring from a sample. You also have uncertainty in the models, because each model is an abstraction of reality. And that's incorporated finally in the conclusions that you make. Now, there's different ways to compare models, and they've been formalized mathematically. And again, there's a little bit of an artistic flair in this as well, because there are certain situations that are better for some comparison tools than others. And it also can be a fundamental, almost religious school of thought, whether you're a Bayesian or completely maximum likelihood. Now, I personally think there's a time and a place for all approaches and all comparisons, and in some are better than others in certain circumstances. So I don't subscribe to the view that one should be Bayesian and one should be only maximum likelihood. To me, the difference is somewhat irrelevant, because if the answer is there, if you have strong enough data set, you'll find it regardless of what approach you use. It's always, in fact, a good practice to take multiple stabs at it from completely different paradigms and different model types, such that if you get a similar answer, you're more likely to believe it. So the approximation of what we call the callback libel, this is from information theory, and I'm no expert in information theory myself, but it states that all models are false because they all represent incomplete approximations of real but unreachable truth, because we can't model the entire universe of possibilities. We have these then Bayesian or dimension-consistent metrics of comparing models. Funnily, well, I guess somewhat ironically, this has nothing to do with true Bayesian approaches. So the weight of evidence of one model is relative to the others, and it assumes that the true model is included in the model set, even though we know it doesn't. It's a bit of a philosophical brain bender, but believe me, there's plenty of good evidence for it. Cross-validation, that's more of the hammer and tongs way to do it. So you take one out, and then you redo your model, and you try to predict the value that you've taken out. Now, as it turns out, cross-validation actually approximates callback libel information, but it's much less this is much more computationally expensive for large data sets than getting an approximation of that information loss. And then there's true Bayesian inference, and this uses Bayes' theorem. And it's basically the posterior distribution, that's the one you're predicting, is based on what we call a Markov chain Monte Carlo simulation. So they're very complex samplers, and they arrive at a distribution based on the data set and the a priori information that you have. They're not a function of an assumed distribution of the underlying error structure. So getting into some brass tacks here. One of the most common, and I think many of you might have heard of it, Okaiki's information criterion, or AIC, and there's variations on that theme. You can have a little subscript C there that controls for small sample sizes, just basically a little tweak that's better for small samples. And it's really straightforward. It's basically 2 times the maximum likelihood plus 2 times the number of parameters in the model. Negative here. So what you're doing is you're adding this together, and the larger the number, the worse the model is relative to the others in the set. Okay? Very straightforward calculation. In the Bayesian information criterion, which is not the true Bayesian Bayes theorem approach, it's a slight change. We're taking the number of parameters times the log, the natural logarithm of the number of data points in the particular data set that you're testing. And there's a very good paper published in 2006, is it, Steve? Lincoln Barker, 2006 in Ecology, that explains the differences between these and when they should be used and when not. It's actually a fascinating paper. I'm more than happy to give you the reference afterwards. And that is the best description I've ever seen of when to apply these two different things. Essentially, to summarize a very involved paper, Bayes' information criterion tends to favor models with more or better predictive capacity. If prediction is your thing, then you might want to go this route. However, if you're more interested in looking at the principal drivers or the most important parameters from amongst the models that you're using, then the Bayesian information criterion tends to pick those out, and you don't get what we call tapering effects dominating. Tapering effects is if you have a lot of different parameters and they all contribute something to what we call the response, which is the thing we're trying to predict, then the Bayes tends to adopt the more complex model without necessarily getting into the heart of the real, most important drivers. And as an ecologist, that's often what we're focused on, the most important drivers of the system. We know that climate has an effect. We know that that temperature does. We know that water availability. We know that the number of individuals in the population does. And we're trying to predict, say, for example, population abundance over time. Some of them are more dominant than others, but we know that they all have an effect at some point in time. Now, a lot of people get confused on what maximum likelihood is. Everyone's heard the term maximum likelihood, right? But who's actually visualized what that means? Does anyone have a very clear definition of what that means? I put one up here. So likelihood is the probability of data given the model is correct. That's its mathematical definition. And the likelihood principle states that the model, given the parameter estimates, is more likely than another if the data for which one. Sorry, that's not very well worded, is it? Well, let me just get my head around that. Then another if the data that you're used for it are more probable. So I left out a few words there. That's my thing. So if you visualize, let's say, just a scatter plot, x versus y. We've all done that before, and we stick a line through it. Can everyone see that line? It's a bit faint there on this screen. And we stick a trend line through there. Then if we just use sort of a least squares approach, we take the difference between this predicted line of best fit and each data point, and we can try to minimize that to get the prediction line. So that's what a least squares regression does. It just adjusts the slope of that and the intercept such that the sum of these are minimized. Okay, very straightforward, but that's the least squares approach. How does, and that's right, you're just trying to, that's your deviation, and you're just trying to minimize the sum of those deviations. In fact, squared, least squares. Now you're comparing this in a multiple working hypothesis sense, but not in a Neyman-Pearson hypothesis framework. You're comparing this to some other model. Now, the easiest model to compare it to is the no-slope model. Okay, so in this case, if the sum of squares of all those deviations are no real different to some sort of fitted trend line, then you don't have support for a trend line. It's that straightforward. But you're comparing it explicitly to this model, which states that there is an intercept but no slope, or the slope is zero, in fact, as opposed to the previous scenario where you've actually had a slope, a meaningful valued slope. It could be up or down, depending on the data, of course. Now, the way maximum likelihood works is that it does the same sort of thing, but instead of trying to minimize the squared distances, it actually fits a distribution to each one. And that distribution, where you maximize the frequency, the probability density, in fact, of each one of these distribution is the fitted model to this particular data set. And so what you're trying to do is in log space, you're trying to minimize that that value, but we call it maximum likelihood because we're trying to get the maximum likelihood from the distribution of each point in the data set. That's maximum likelihood. It's often, so there's the likelihood function for each point, and we just get the max as the product of these likelihood functions. Maximum likelihood, just as a bit of a background. Okay, that's sort of, we won't go into all that. This is the minimization. I was probably, when you take the log of that, because it's a probability density function, it becomes negative. So you're trying to minimize that. That's really the functionality behind the maximum likelihood approach. Now, something people say, okay, well, the reviewer asked me for a p-value to test something, and you know, if you're a stickler like me, I tell them to bugger off because I say the p-value is absolutely meaningless. Under certain circumstances, I'll admit there are some uses for it, but usually in a resampling process. But we won't talk much about resampling today. But the alternative, which is more in the philosophy of multiple working hypotheses, we invoke what we call the evidence ratio. Now, it's really just the evidence of one model versus another. It's very simple. It's a binary comparison in this case, but you're explicitly testing the alternative. In this case, you establish what the alternative will be. So how much more likely, given the bias correction, remember this is a parsimony core, and the bias correction here is the number of parameters, remember we're talking about maximizing parsimony, is of model, how much more likely given bias correction is model 2 than model 1. So if we get a Akaki's information criterion weight, now weight is simply a way of expressing that as a function of all the models in the model set. So if you have one model out of 10 that has 90% of the support, all the model weights add up to 1, meaning that that has 90% relative support compared to all other models. But if I want to say compare model 1 to model 2, then I can take, so in these three cases, I've got three models. They all have weights. So this one has the strongest or highest model weight. They all sum to 1. So 0.046, 0.942, and 0.012, they sum to 1. This, after correcting for, as I said, the number of parameters in that model, has the highest weight. So the evidence ratio of model 2 to model 1 is simply the division, which means that model 2 has 20.5 times more support than model 1. Now, I mean, I could bank on that. I'd say that's pretty good evidence. If it's twice as likely, given the bias correction, you know, that's substantially weaker, of course. But you see what I'm saying? There's no threshold here. You know, if they're about 1, you know, then you say, well, there's not a lot of evidence that one has more evidence than the other. So I'm not really going to put a lot of emphasis on that particular comparison or that hypothesis test. If you're getting up to, you know, it's got 6,000 times more support than that one. A really good concrete example is the one I showed previously when you've got just a simple XY scatter plot, you fit a trend line through, and then you compare that to the null model with the zero slope. Now, if the trend line model has a lot more support than the zero slope, then you can say, well, yes, there's a trend line, and you can quantify it. It has 20.5 times more bias-corrected support than the null or the zero slope model. Lovely, isn't it? It's intuitive. It doesn't require any sort of arbitrary thresholds. And it's, again, it's a very, you're only comparing one thing at a time, of course. And so the temptation is to do evidence ratios all over the place, but then you get into the problem of spurious statistical evidence when you've just done a lot of tests. Because every once in a while, if you do a lot of tests, every once in a while you come up with a false positive or a false negative just by doing lots of tests. But we won't talk about those kind of corrections here. But the true power of multiple working hypotheses isn't so much in the comparison of two models or the binary approach. It's using the full uncertainty in your model set to derive your parameter estimates. So in this case, we take predictions from the model, because all models will, once quantified, will allow you to predict something based on its own data set. You get parameter estimates, and then you can feed in whatever data you might have. It could be a validation set. It could be the same one that's jackknifed. There's all sorts of approaches. But and this is a simple one. The mass of the individual is a function of its sex, its age, and its body morph. Okay, these are three things. These are three hypotheses. Now it's just a subsets. In this case, we're only considering sex and age. In this case, I think sex is the most important predictor of mass. Now, once we estimate these, we get a comparison metric like an Akaki's information criterion weight. We get a parameter estimate for each one of these particular parameters. So we've got a beta, that should be a little beta hat, we'll get an estimate on that. And then we've got for each, obviously age and morph aren't in this particular model. But if we look at, if based on the previous Akaki's information criteria that I showed you before, the model 1, model 2, model 3, if you recall, model 2 had the most support. So I take the prediction from model 1 is that females will have a mass of 160.2 grams. I multiply that by the information, the Akaki's information criterion weight, which is essentially a model probability. You can think of it in that light. And then I add that to the prediction from model 2 and its weight. And then I add that to the prediction from model 3 and its weight. As you can see, model 3 has a very low prediction. Again, we're only considering the sex component here because we're just looking at the female predictions. But this is partialed out the effect of sex from these other potential parameters. That's why we can compare them directly among models. It's a multivariate model. And then we get what's known as a model averaged prediction. Now at this point we haven't included the uncertainty associated with each parameter estimate in each model, but it's just a demonstration that you're getting the weighted prediction based on the relative evidence of each model in the set. Very powerful thing to do, and I'll show you some examples of that a little bit later. Now there's ways of incorporating the uncertainty associated with each beta parameter for the sex factor in this case. But this just shows you that if I had based my prediction on a single model of my choice for no particular reason, I would have got quite a different response. For example, if I had chosen this because it was more complex, then I would have had a much lower prediction of female mass than I ended up with. This approximates truth much better than just focusing on a single model. Because by choosing a single model only, you necessarily make sometimes a subconscious decision to exclude the rest of the universe's possibilities, and therefore you're making a value judgment, therefore it's not science. Now briefly, I'm not a Bayesian myself. As I said, I don't like to call myself any of those particular things because I think it boxes people up. A lot of people have adopted Bayesian approaches. I think they're far superior to anything maximum likelihood can throw at you, but I disagree. I think there's a time and a place for everything. But so just briefly, I'll introduce it here to be aware of it, because some people will insist you approach it this way. Now they do have specific cases where they're certainly superior. For example, some work I've done with Steve Deline over there. We looked at predicting the rate of population increase of a whole set of mammals, and based on their allometric predictions of weight their allometric predictions of their intrinsic population growth. That means that we could predict what their population maximum growth should be based on their size. There's some a priori information there. So we incorporated that a priori information into a model that was trying to predict the shape function of a density feedback mechanism. I'm probably losing you a lot on that. That's okay. But we were able to use a completely independent prior set of information plus some new data to predict or update a model and get something called a posterior, which is the model's prediction. So what you're doing here, and I always give this is a great example. I say all people are Bayesians just by nature. Who here crossed a road to come here today? Just hands up. Say most of you. Okay. Had you crossed that road before, those people who put their hands up? How many had crossed that road before? Okay, well, you're all Bayesians, because what you've done is that because you've crossed that road before, you have an a priori distribution of the kind of traffic and the conditions that are normal for that part of the road that you crossed. Now, you take that prior and you approach, as you would this morning, you come to the road and you collect a new data set, and that's the traffic flow, that's the weather, that's how you're feeling. And then you make a model and you predict the chances that you'll die when crossing that road. Okay, so you updated that prior information with the new data you've just collected. You then make a prediction of the probability of dying And then you validate that by crossing the road. Okay? So you're all Bayesians. You can see how that works. It's a more intuitive way of thinking, and that's why a lot of people adopt the Bayesian approach as a more natural way of testing things. So under likelihood theory, it's the probability of the data given that the model is correct. And this is how we state it mathematically. Whereas the Bayesian flips it entirely around. It says, what's the probability that the hypothesis is true given the data? Okay, so it's a complete philosophical shift in how you approach. It's very attractive to some people, and in some situations, as I said, when you have really good prior information that you can incorporate formally into the posterior or the prediction, it has very powerful advantages. The principal one being that it reduces uncertainty in your prediction. So you might have a prediction, and it could be very, very similar between likelihood and Bayesian, but because you can invoke that prior information formally, you can reduce the uncertainty of the resultant posterior or predicted value of your models. The same essential philosophy of multiple working hypotheses applies to both likelihood and Bayesian. You can pose multiple Bayesian models, and you can pose multiple likelihood models. Because these are based on specific distributions, the measures of model performance are usually a little bit easier to calculate. Whereas in the Bayesian sense, even the number of parameters can get uncertain because you're using a resampling process essentially through multiple chains. And I won't get into the details, but it means that having a model with a specific number of parameters gets very dicey. But it can be done. Why Bayesian? Again, these are sort of things that sort of all the Bayesians will say to you. It aims to answer the questions of interest directly because you're posing it in a completely different way. You're updating the hypothesis based on the data. It does allow a more complex set of models to be fitted, usually because they're non-distributional. And if you have to shovel something into a distribution, and a particular error distribution as maximum likelihood requires you to, sometimes that can get messy, especially in multivariate space. And it uses all the information transparently. Sometimes maximum likelihood gets caught in little, local minima. You can think about this multi-dimensional valleys and mountains, and it gets stuck in a little corner of that multi-dimensional space, and it can't estimate its way out of it. Whereas Bayesian is a bit better at getting yourself around those kind of local minima, it's called. So the good, it does provide probabilistic interpretations. It's logically consistent to update the prior knowledge, and the uncertainty is associated directly in the model. It does use prior knowledge as opposed to the, as I talked about before, the artistic flair of posing the most intuitive set of models. That's a component of Bayesian as well, but because you have that formalized incorporation of that prior knowledge, it can be very powerful. And then these mathematical Markov chain Monte Carlo approaches can be invoked with general purpose software, and you can even do it in R quite easily now these days. The bad component is that it does need the prior knowledge, and even uninformative priors can lead you down the path to a lot of computational effort for little benefit compared to maximum likelihood. Priors are seldom unequivocal, so just be warned that you can weight your final outcome based on where you started, depending on the strength of the data, the new data set that you're claiming to, or you're using to update the prior. Yeah, just a little bit, these non-informative priors. So essentially you're not using any real data, you're just giving it a maximum sort of universe of possibilities. It gets to the point where it gets a little bit mythical. As I said, if the data on the prior are poor or not as extensive of the prior, then you essentially just end up with the prior. So it doesn't really give you any new information. This is getting better and better these days. Maximum likelihood is really good at evaluating model performance and where you screw up, essentially, and where the data fall apart and the model isn't very good. The diagnostics are really good, things like QQ plots looking for normality. And sensitivity tests are generally less developed from Bayesian, although that's changing. And sensitivity is a good way to see what's the most important component of your model post-hoc. We won't go into sensitivity analyses today. And finally, the ugly, just the MCMC. If it's not appropriately initialized, you can get caught in all sorts of horrible places that you don't want to even contemplate here, especially if you're not very comfortable with modeling in the first place. My advice, if you're going to do some Bayesian approaches, make sure you use it with a Bayesian sitting beside you who's done this sort of thing before. It's not as easy to pick up. But I don't want you to turn you off of it either, because it has some very important advantages. Now, common statistical tests that you've learned back in your undergraduate, maybe even before that. So the t-test asks the question, given the inherent variability of my samples, does the mean of a treatment equal the mean of a control? Very straightforward. You've got ANOVAs, analysis of variance. It's a similar principle to the t-test, only you're looking at the variances as opposed to the means. And then regression relates, as I said, to a continuous variable to a dependent one. The last two are forms of a general linear model. The only difference is that they've assumed a particular underlying distribution, in this case normal, and they have associated sets of assumptions like the equality of variances in the case of ANOVA. Okay, but what if your question is nonlinear, and what if it's non-Gaussian, non-normal? What do? Well, general linear models assume, and this is the difference between generalized and general. General linear models mean a Gaussian error distribution. You're assuming automatically. That's why ANOVA is essentially a GLM. But you can take the generalized form and apply a particular error distribution based on the type of data. We'll go into that in a little bit. And you can also describe the relationship between the mean and the linear predictor via a link function. It gives you more power to account for these often the assumption problems that you have in a simple ANOVA or a t-test. You've got the variance function itself. It can be fitted using iteratively reweighted least squares, which is an approximation of maximum likelihood. And this is basically a way of getting around a lot of computational time and effort. And you can fit nonlinear generalizations of linear fits quite easily, which is nice, which you can't do with an ANOVA, for example. So the general structure of a GLM, oops, sorry, gone too far there. What is that? That should be, that's sort of bumped around a bit. I apologize. Let's just go. What have I done? Okay, I guess I thought there was something here. Anyway, you're going to get, the simplest thing is that the error structure is Gaussian with a predicted mean of 0 and a variance that's constant. And the y, which is the predicted value, takes values over a limited range. And y can be count data, for example, non-negative integers, or categorical or discrete values. So you can mix and match. You can have categorical. I'm way behind. Do you guys want to keep going a little bit longer? Is that okay? Because okay, if there's someone coming behind us, we might have to vacate. But I think I might have to give you another one of these because I haven't even.
Oh, would you be correct?
Is there someone there?
We'd love to. That's it.
I'll just continue. So you can mix and match. You can have factors. You can have continuous variables, and you can have different types of data sets in there. The change in mean brings about a change in the variance of y here. That's essentially the underlying dynamics. So how is it constructed? Well, you have a predicted mean here, which is some intercept, followed by a coefficient estimated for each parameter in the model. And as I said, you can have you have multivariate models that are quite complex, plus some sort of error. There's the error. That's the noise, and it follows a particular distribution. And the probability density function of y is a function of the mean, where the mean is predicted from the data themselves. Now, the probability distribution function depends on the data distribution, as I said, for Poisson or binomial. And that will lead you to fit a link function. Sorry, that's unrelated to the error distribution. But you can pick a link function that allows you to parameterize that relationship between the mean and the predictor. So commonly used in GLMs are all sorts of different distributions. You have the standard Gaussian, so then it defaults to a general linear model. You have Bernoulli distributions. You can have binomial, Poisson for count data. Anything that you count that's an integer and a single individual, you essentially have a Poisson distribution where the mean is equal to the variance. Gamma distributions, which are a little bit more complex versions of Gaussian, but they tend to tail off in the smaller values. And you can have inverse Gaussian distributions, which have a specific kind of form. And all of them can be applied based on the data set. Now, often it's somewhat of a post hoc process where you're trying to find the best error distribution for your data, but it allows you the flexibility of doing so such that your model can estimate the parameters appropriately, which in ANOVA, if it's non-Gaussian, it cannot. Okay, just to summarize there, so we've got the linear, logistic, and Poisson regressions can rely on normal distributions that are continuous response. Binomial, so you have a yes-no kind of scenario where you're fitting a logistic function between the 0 and 1. The discrete response was the Poisson. All these are forms of GLM. Now, the estimated parameters are all partial in a GLM, in that, as I said before, once you've accounted for all the other multivariate explanation or explanatory power of the other variables in the model, you partial out what that particular variable's contribution is to the prediction. And I won't bother with the last bit. Now, there's some terminology that should be commonly understood, because there's a lot of, some of you may have heard of the, I guess, the more complex version of a general linear model or generalized linear model. It's the general linear mixed effects model, or mixed models. Now, most models that you pose have a particular, I think we do have people lining up. Can we just check that?
Yeah, when I checked, they were just waiting for next door. This one?
Next door?
Yeah.
Oh, okay.
So I think we're okay. You guys waiting for 16?
Okay,
We're
good.
waiting 16,
So the fixed effects are usually the parameters of particular interest that we're trying to test explicitly. Whereas you can get cases where, and the assumption of all of these models is that your units are independent, and that there isn't some underlying correlative structure of those units. Now that's a hard one to get sometimes, especially if you can think about, especially if you think about spatially related units. For example, all of Australians live in Australia, and therefore we have a particular way of looking at things, particular way of behaving relative to all people in New Zealand or all people in Indonesia. Now, if you just took a random subset of Indonesians, Australians, and New Zealanders, we might have some sort of internal correlation structure that will affect the prediction in ways that you haven't tested explicitly. That non-independence can be accounted for by including a random effect. In this case, the example I just gave you would be country of origin. There is some underlying correlative structure that you're not necessarily aware of on how strong it is, but you know that those examples are non-independent, and therefore they can lead to erroneous conclusions if just without any sort of consideration of them. In other words, they'll affect your fixed effects parameters. Repeated measures and split plots are also sort of ways of using GLMMs, and they have both the fixed and the random effects, as I said. So you have a series of fixed effects, and then you have, based on the available information, a series of usually categorical, although not necessarily always depending on the model structure, using categorical random effects, as I said, for example, country of origin. The other problem with this is that the likelihoods and the parameter estimates that you get are only proximate. Now, it turns out that in the Bayesian sense they're perfect. They were estimated exactly, but generally this isn't a big deal if you have a decent sized data set. You can get fairly close. You can fit both of these, GLMs and GLMMs, using maximum likelihood or Bayesian inference. Sometimes the GLMM can be problematic with maximum likelihood because, as I said, they're only quasi-likelihood and approximate parameter estimates. That's the approximate K. The models can be contrasted with information criteria. So it's, again, a multiple working hypotheses approach. They're fully flexible for covariates, factors, fixed and random effects, which is nice because it's a big mishmash of the universe of possible influences. Fully flexible for distributions, as I said, and they can be compared to other model outputs. Now, if we're not running too far, I'll just give you some examples of some of the work that I've been involved with. So several years, I guess getting into 6 years ago now, looking at the difference between species based on the probability of either becoming threatened or becoming invasive, or not really having anything to do with our human value judgment of those things. We took, in this case, we took a large group of plants from the second most specious plant group, the legumes of Fabaceae. So all acacias, for example, are Fabaceae. Most of the nitrogen fixers are legumes. There was really controversy there as to which intrinsic traits of these plants led it to become more likely to either be threatened or invasive. So what we did is we did a GLMM approach where we took out the non-randomness as best we could. In this case, there's probably better ways to do it that I know now, but I did this quite a while ago, where we took the phylogeny, i.e. the relationship between species, because species aren't random things in space. They come from lineages, so things that are more closely related are more likely to have the same kind of traits. So that won't necessarily affect their ecological function in the same ways, but they're more likely to have that phylogenetic baggage with them. So we accounted for that by including a random effect of the subfamily of tribe, and we tested whether they're threatened or not, so a binomial model, or invasive or not, or threatened or invasive. So we took all the ones that were neutral. All binomial models. And then our correlates were range size, habitat type, reproductive mode, dispersal capacity, all these different things. And we came up with this set of compared models. So in this case, we used both AIC and BIC. So these are the weights. So this model had, as you can see, had the most support under BIC, but there was less support for it using AIC. That's because of tapering effects. So we had also, you can predict the amount of variance explained by that combination of parameters in the response, in this case either being threatened or not, or invasive or not, or threatened or invasive. So 3 different model sets. And we're explaining consistently about 16% of the variance. That means that most of the variation isn't being explained by our particular variables. But in ecological systems, that's actually not so bad. If we can get any explanatory power whatsoever, we're usually feeling fairly good. And so we had, the geographic range, habitat, altitude, all these things had some sort of effect, and they were supported by the top-ranked models, where growth and habitat growth, habit, and height having a smaller effect. We've done this for amphibians as well, so we did a lot of this trait-based extinction risk stuff. These are all published. You can look at them and see what we did. So again, we're getting models, body size, range size, and we're predicting, in this case, we're getting substantially more predictive capacity, up to nearly 50%. And here's the number of parameters for each model, the likelihood, and then we establish this is a Bayesian information criterion. So this model, having body size and range size, had the most effect. So basically, you can predict whether or not an amphibian is going to go extinct or not, mostly based on its range size, and to a lesser effect its body size, with all these other things having tapering effects. So we could identify quite clearly that the bigger range that a species had, the less likely it was going to go extinct. It seems like a bit of a no-brainer, but back when we were doing this sort of things, people were looking for trait-based predictions so that they could say, well, we should put more conservation effort on big frogs, or frogs that have very limited range sizes. It's a very applied sort of approach. We've done it for sharks as well, with similar sorts of conclusions. You can see here, these are modifications of prediction of the threat risk based on particular combinations of those variables. Now, another great use for general linear models and generalized linear models, and there's a whole host of different models you can use, are things like species distribution models. So this is a prediction of the world habitat, I guess the habitat suitability, I guess is one good word for it, whale sharks around the world based on samples associated with the tuna fisheries. This is what my student Shiketa did earlier this year. And so this is all the world basins, different seasons of the year, so January to March, April, June, and so forth. And then she put in a climate prediction on sea surface temperatures, because one of the principal determinants of that distribution was sea surface temperature. And we got the distribution, or the habitat suitability prediction for 2100, and the take-home message that a lot of that range starts to shrink up, because they're not tracking necessarily the we don't know anything about adaptation or tracking, but we do know that the available suitable habitat, if all things stay the same, it's going to be less in the future for whale sharks. So that was just published yearly. So the standard species distribution model, but it accounts for things like spatial autocorrelation and time series that have these associated correlations inside the data set. We've done it for species richness in the Great Barrier Reef. Again, samples of coral reef fish at specific sites over the last 15 years, divers coming through saying we saw this many fish, associating that with distance to shore, latitude, substratum type off the reef, whether the reef was inner or outer or closer to the shore. And then we can make a prediction of the number of species we'd expect to see across all reefs, because of course we're not going to be sampling all 3,000 or so reefs in the Great Barrier Reef. That would be impossible. And then we can incorporate the uncertainty with both the parameters and the model uncertainty from our model sets directly with the, in this case, demonstrated by the strength of the particular color. So we have variation on this sense, and we have estimate of the mean number of species on that. So again, it's not really a species distribution model, but we're predicting in this case richness based on some physical properties of those those reefs in the Great Barrier Reef. Very, very useful approach, and it's been done for a lot of taxa now. Other ways I've done it too, using GLMs, in this case mixed effects models as well, looking at floods across the developing world. Just as example, many hundreds of thousands of people are killed and millions are displaced every decade by severe floods. Lots of damages, that sort of thing. So we took, there's a relationship hypothesized between forest loss and flooding frequency and duration. We took the habitat loss, forest loss in all these countries, and we controlled for things like that's the slope of the landscape, how much rainfall or precipitation they receive, and then the soil structure based on those countries. And once you partial all those things out, the natural forest cover, the more that you have, the less likely you are to have a flooding event based on the flooding frequency, and to a lesser extent, the duration is even lower. So we can come up to people and say, don't cut down your forests because more people will die and it'll cost you a lot more money, which is a lot stronger argument than saying, protect all the species because we love them. A variation on that theme, instead of using generalized linear models, using phylogenetic least squares options, and this is stuff I've been involved with Steve. And Steve did a lot of the modeling for this, in fact, looking at the range size or area of occupancy for British birds over the last 30 years and how they've shifted. And some of them increased and some of them decreased in their range area over those 30 years. And so we called those the contractors that went down and the expanders that went up. And related to their threat category, the conclusion was, though, that not all things that are threatened are declining and not all things that are doing okay are expanding or staying the same. We had some contracting, some going easier. So we wanted to know what was going on. Now, this is a case where we use model average parameter estimates across all models, and fairly seriously complex component of what predicted that change. So these are the model averaged standardized coefficients from the models, all across all models. And it's a really nice way to compare the relative effects of models on different parameters on different scales, but incorporating the entire model uncertainty. So I'll just give you an example. In this case, the February temperature, this is a nonlinear response because it was a quadratic. So it was a humped-shaped association with February minimum temperature. Had a large effect on whether a species was likely to change its area of occupancy, but in both directions. So the colder it was, the greater the temperature, the more that they expanded in the north, and the more they contracted in the north. And it was exactly the opposite in the southern distribution. Getting some very complex things going on here. There was effects of how fragmented the population was, some precipitation effects, and whether there was a dispersal, the natal dispersal capacity and body mass. In essence, we took a very, very complex series of questions with all sorts of statistical nightmare components to it and managed to tease out some very complex descriptors of what happened. Now, I invite you to read the paper if you're seriously interested, but it was one of the most complex papers I've ever been involved with in terms of the interpretation. I'm going to skip over this because we're seriously running out of time. I want to jump right to the matrix stuff and get to the... We don't need to see all this. Okay, where are we? That should be up there already. Why is that not coming up? Where did my values go? They're gone. My matrices are gone. Okay, well, you can see that, can't you? It's a bit small. It doesn't like to come up on the screen for some reason. That's too big. Now, projecting populations through time is another bastion of ecology. So if you have some sort of, it can be a threatened population, it can be something that you're harvesting like a fish population, it can even be us. How many people are going to be in 2050 or 2100? And you may have seen some news about that last week. One of the stock standard ways of doing that is called a matrix model. It's very simple. It's a transition matrix. So the probability of, in this case, let's say that the 1, 2, 3, 4, 5 subscripts are years, age, so they're discrete age units. The probability of transitioning from age 0 to 1 is probability S1, which is the survival. So the probability that you'll survive from birth to age 1 is S1, and so forth and so forth. And then we invoke a fertility component here. That's the probability of producing individuals in this class based on your age. So these are ages here. And you can see it's a n by n matrix. In this case, this is omega, so this is the longevity of the particular species you have, and it goes all the way through. So you transition from one state to the next, and you produce new individuals that start out in this state and then they progress through. Now, standard matrix algebra allows you then to multiply that by a population vector, so these are the number of individuals in each age class. And then for each time step, and that could be a year in this case if it's an age-specific one, so we're going from year to year to year, I just keep multiplying this matrix by an updated population vector. So, for example, if the population is growing, multiplying this by that will give me a new population vector that's slightly smaller, or slightly larger, with more individuals in each one, and then I multiply that to the base matrix and so on and so on and so forth. And you can project into the future that way. Now, you can have uncertainty in all these parameters, and you can subsample from those, or you can do it deterministically and ignore the variation. Some ways you can do that, sorry. Let me just start this up again. There's some great software. That's my daughter. Sorry. There we go. Vortex is a freely available bit of software. It's actually an individual-based model, and it sort of emulates the matrix approach, but it's very powerful, and it's essentially the same thing. You can go on to, it's very easy to use. It's designed for non-modelers, but it has amazing flexibility and power now. And we've done things like also mixed up Vortex with epidemiological models, and I have a student over here, Wayne Boardman, who's going to be doing exactly those sorts of things. So you get individuals getting diseased and then passing it on to other individuals and then pumping that back into the Vortex model, having that run for a particular set of time. And that's all communicated to this thing called Meta-Model Manager that allows two different timescale models to talk to each other. Very powerful modeling approach, and you can read about some of the applications we've done for that. In this case, that was for buffalo and TB in the Northern Territory. Now, there are other software things out there. There's RAMAS GIS, which is a spatially explicit metapopulation cohort-based model, so it's using the matrix approach again, but in this case you have specific subpopulations that are connected by some sort of connectivity, dispersal rates, that sort of thing. They're connected to a landscape type, and then you can manipulate the landscape, for example, let's say climate change reduction in range, and that then subsequently affects the subpopulations that talk to each other, and then those go through their different life cycles. MATLAB, I started out doing matrix models in MATLAB because MATLAB is specifically designed for matrix algebra, amongst other things. But everything you can do in MATLAB, you can do in R, and R's free and MATLAB's very expensive. So that's why. So I do all my matrix modeling these days in R with some applications in Vortex. So a recent example was a Vortex. One student, Tom Prouse, published looking at how human intensification, climate change, and the interaction between thylacines, devils, and dingoes affected the persistence probability of thylacines and devils on the mainland. As you know, there aren't any thylacines anymore, and the devils went extinct about 5,000 years ago on the mainland. They persist today in Tasmania, but they're not doing so well. And we wanted to ask the question whether dingoes or human intensification, that means through increasing human population size and technological capacity, and climate could explain more of what we would explain the extinction of those two species. As it turns out, again, when you're doing a multitude of models, these are all vortex-based, these are all interaction between multiple species. The human intensification variable has far more likelihood of evoking that extinction than any of the other components. And in fact, the dingo, which is blamed for the extinction of those two species, had very little effect whatsoever. So it's a way of looking back in time when you don't have the data by constructing complete functioning ecosystems, again, a simplification of reality, to pose some really interesting hypotheses. We've done that with predicting climate change effects on commercial species in South Australia aquaculture. And a paper that's going to come out very shortly of mine and Barry Brooks is we projected the human population to 2100 and looked at various scenarios of fertility reduction and wars and catastrophes. I won't show the wars here because we're killing 2 billion to 6 billion people virtually. It was a lot of fun to do, but it's ethically questionable in public. That's coming out shortly, but in this case we can pose some questions about what are the effectiveness of different fertility trajectories on the final population size, and what works and what really doesn't. So it has a lot of applications. So, summing up, last slide, sorry to keep you so long. I've talked a lot about this philosophy and the different approaches in this book chapter. In this book, the book's free. You can download all the PDFs. I've written a blog about it, and all the links are there, so you can download that chapter. It's fairly long. I think it's about 30 pages of fairly tight text, but it's a nice little reference thing. And then, we mentioned these kinds of textbooks in there, but some of the things that have really influenced my career, Morris and Dirk's Quantitative Conservation Biology, certainly Caswell's Matrix Population Models book is essential, but it's like reading, it's like reading Latin. It can be very hard going. First 2 chapters are great, and then it breaks down into serious geekdom. Model selection, multimodal inference. Burnham and Anderson's classic paradigm-shifting text. It talks about multiple working hypotheses and model ranking and how to calculate and how to do it. And then ecological models and data in R by Benjamin Bolker, a really hands-on recipe-based approach to dealing with all sorts of problems. I don't agree with a lot of Bolker's approaches, but at least he's got sort of the technical recipe in front of you that you can follow that I couldn't give you today. There are plenty more out there. Read that chapter. I give some other examples of books that can be useful depending on your interests and your needs. But take-home message again, I said at the beginning, nothing can replace practice. Sit down with someone who knows something about this. Take some old code and play with it yourself, but you absolutely have to sit down there and play with your own data. There's no replacement for it. No one can teach you how to model otherwise. So with that, thank you very much, and sorry for going over time.
Thanks, Corey.
Questions? I covered a lot of material, and I did go fast, and I'm sorry for that. But really, the best thing you can do is just be aware of these things. I've talked to you a lot about sort of the main issues to be aware of. Now it's for you to go down and say, but these are my questions, these are the type of data I have. I need to get these techniques, and I need to figure out how to do them and code them. Certainly R is your starting point. If you're not using R now, you should be. And if you don't feel comfortable with it, sorry, you're going to have to get it comfortable, because that is one of the best platforms. It's free. There's a massive community using it. Almost every ecologist uses it now. And you can link almost anything to it. I do almost everything in R. And it's not the most efficient modeling in the world. I mean, if you're a real programmer, a lot of programmers will scoff at R, but that's not the point. Most of us aren't programmers. We're users. And it's really easy to debug, and there's plenty of examples where you can steal code and update it for yourself. And that's perfectly reasonable as long as you cite the person in question. So do that, and continue to go to these things, because you know what? You're not going to get this any other way. So this is a great initiative, and I Jasmine and David and amongst others have been fantastic and instrumental in this, and I really want to see this succeed, because I think our mathematical prowess is lower than it should be at this stage in one's career. So thanks. Good luck.
Thanks, Gordon.